So I'm gonna do one class and give you the other one if you want to review for your midterm. And some of you maybe will be driving to the college. So we'll do the first hour, then I'll give you the second hour for reviewing or anything. And the other thing that you got your room number, right? You know it's 11:30, the midterm today. It's going to be an hour and a half. It's going to be 10 questions. You're going to spend about 5 to 10 minutes on each question. Some of the questions are very short, let's say. They're not going to take more than 3-4 minutes, but let's say 5 to 10 minutes per question. The questions that they will take time, the questions that where you want to find equivalent circuit and we want to do mesh analysis or nodal analysis. Nodal analysis is going to be one equation. Mesh analysis is going to be one equation and the other one is pretty easy. So kind of both of them will be one equation. I mean, the mesh analysis is going to be two equations, but one of them is very easy to solve. The equivalent circuits, I think one of them is DC, one of them is AC. So you have to find north and you have to find Thevenin. Some of the questions are not, they're not going to need a lot of calculation, let's say it that way. They're not going to need a lot of calculation. So find the voltage across the resistance, find the voltage across that element. Why is the current going through that? Why is the current in RL or something like that? So those questions, they don't need equations or anything. You just look at the question, one step, you're going to find the answer. Anyhow, so we will start lesson 8. We will do some maybe 50% of it today. So three-phase circuits, it means before in the last class in lesson 7, what we did three-phase sources. Basically, we did talk about the delta connection, the Y connection, the relationship between phase values and line values in each connection, Y or delta. Now we're going to actually have a full circuit and we're going to find the currents and voltages in this circuit. And the circuit is going to be a three-phase circuit. So these are just the connections, just to remind you that not just the source can be connected Y or delta, the load as well can be connected Y or delta. So this is Y connected load and this is delta connected load. What we're going to do, we're going to always do balanced system. So the load will be balanced. What is a balanced load? Phase impedances are equal. Magnitude and in phase. It means this will be exactly like this impedance. This will be exactly like the third impedance. So the three impedances are equal. So if the first impedance is 3 plus J4, the other two impedances will be the same thing. So per phase impedance are equal. So the per phase impedances are equal. Same here. So this is a condition for balanced load, and we're only doing balanced loads. We're not doing unbalanced. So the common case is balanced and balanced. If you are going into the electrical department, if you're electrical, you're going to actually do at some point unbalanced, okay, in power system courses. So because we have two options for the source, it can be connected to either Y or delta. The load can be connected either Y or delta. So as a circuit, source and the load, you can have Y, maybe Y delta, delta Y, delta delta. So Y means the source is connected Y, the load is connected Y. Y delta means the source is connected Y and the load is connected delta. So I have 4 options. We're gonna go through these 4 options. Now this is the easiest to analyze. This is very common. So those are the ones that we're gonna focus on more than these ones. Now, when we do the analysis to these ones, sometimes we actually change them into all of them. Actually, the 3, we change them to YY. So we can do the analysis easy. You will see that this might be sound difficult 3-phase circuit, but the analysis, especially in YY connection, is not actually difficult as once you know the basic concepts. So this is the YY connection. What does that mean? The source is connected Y. The load is connected Y. And there is a line in between. So it cannot be more complicated than this in YY connection. So what you have the source, internal impedance of the source. So internal impedance, sources sometimes they have internal impedance, and it's considered in the calculation. The transmission line has an impedance, the line that between the source and the load, and the load has impedance as well. Now, sometimes you have a neutral to neutral connection, this wire, and since it's wire, will have impedance as well. But this is not going to affect my calculation. The reason that current IA going this way, current IB going this way, current IC going this way, they're going to go here in the load. And what will happen once they come in, they will leave as IN going back. But the sum of the 3 currents will be 0, so IN will be 0. In balanced system, IN is 0. Because at this node, you have coming currents. Let's say all of them are coming. So IA plus IB plus IC plus IN, they're all coming to the node. Okay, this node here. Nothing is leaving. They're all coming. Okay. Now IA plus IB plus IC, the sum of these 3 is 0. So that means IN will equal to 0. We know that in balanced system, IA, IB, IC, if you add them, they're gonna be 0. If 5 angle 0, 5 angle minus 120, 5 angle plus 120, if you add these 3 currents, this is just an example, you're gonna get 0. You can try that in your calculator. So in balanced system, the sum of the 3 line currents or the 3 phase currents is going to be 0. The sum of the phase voltage is going to be 0. The sum of the line voltage is going to be 0. The 3 of them. It's always 0 because they always have 120 degree between them and they have the same magnitude. So the point here, this line is not going to affect my calculation. Only affects my calculation if the system is not balanced. So now this doesn't matter. You see it, it's there or not there. For us, it's not gonna matter. Okay. Now, why do they have it? They have it in case that the balanced is lost. The balanced load is lost or system. So if the current here and current here and current here, they're not equal in magnitude, what you have, you're gonna have current going through the neutral. So for us, balanced system, the neutral current is 0. The neutral line is not going to affect my calculation. Now, how do we do the analysis here? Very basic. The first step is very basic and simple. Take single phase circuit. What is a single phase circuit? From the neutral to the neutral. This is one phase, right? Take single phase circuit and find the line current in this circuit. This is the line current. Once you find the line current, you can use it to find everything else. So we will see this. Okay, just a few information. The phase values, the line values. We know that the on Y connection, the line voltage is square root of 3 times the phase voltage, and you add 30 degree. So you're gonna add 30 degree. Okay. This is the one-phase circuit. And this circuit, I can find this current by total voltage divided by the total impedance. And this is the single phase equivalent circuit when I simplify it. Now, when we see the question, it's not, so this is, in this question says calculate the line currents. What does that mean? They're gonna look for the three line currents, IA, IB, and IC. In the line, this is the line, not in the load or in the source here. There's three currents. This is what the question says. Now, first thing we have to see, what kind of connection do we have? We know we only have balanced, so we don't need even to check for the unbalanced, because I'm not going to give you unbalanced system. And balanced means, just for the future, voltages are just equal in magnitude. Phase shift is 120. Loads are equal. The three loads, 1, 2, 3, they're equal, exactly the same. Transmission line impedance, they're the same. Okay. Then you can say the system is balanced. Now this is Y to Y connection because the load is connected Y and the source is connected Y. This is the load, as this is the source, Y connection, and this is the load is Y connection. And this is the transmission line where the lines here. So one more time. This is the load. Look at the connection, it's Y. This is the source. This is the load. Look at the connection, it's Y. Now someone would be like, this is like this. But still Y, it looks like, you can just say it looks like this. You just, the arm is like that. So this is still Y connection. So Y to Y connection, how do we analyze it? We take single phase circuit. Single phase circuit. And what is the single phase? From the neutral point to the neutral point. Assuming it's a balanced, means the neutral here is 0 volt, the neutral here is 0 volt, so this is the same. So this is how I do it. I'm gonna go from the neutral, go through one phase until I get to the neutral of the load. So I go through, I go here, oops. I'm gonna go through the source, this one, the impedance of the line, this one, then the load impedance, then I reach the neutral, this one. Now this is the circuit I have. This is called single phase equivalent circuit. So please don't make it complicated. Whenever you see Y to Y connection, just go take one single phase from neutral to neutral and draw it. You have to draw it. If you don't draw it, you're not gonna see it. Then this circuit, you're gonna find the current in the circuit, and it's the line current, IA. How to find the current here? Voltage divided by the total impedance. This is gonna be even in your midterm today, something like this. So voltage divided by the total impedance, okay? So if you have an impedance here, add them up. How do you add? Real with the real, or you can just plug in them in your calculator. 5 plus 10, those are the real, they give you 15. Minus 2 and 8J, when you add them, they give you 6. Now you have this basic circuit. So what you're gonna see in the midterm today, something similar. It says find the current here. Maybe this is only 10 like that, without this. So what you're gonna do, you're gonna do 5 plus 10, and this is the same because it doesn't have J here. So it's just 5 minus J2 plus 10. This is the total, so it's 15 minus J2. This is the total impedance, and you divide the voltage by this impedance, gives you the current. Is this okay, finding the current in this circuit? Just the total voltage divided by the total impedance. I'm afraid that people will not do the easy questions. Is this okay? Any questions here? Any questions? So as I said, this is going to be similar to one of the questions you're going to see. It says find the line current. Okay. Now, we'll continue. This is the circuit I have. The current IA is actually voltage divided by the total impedance. Then I find the first line current. Once I find the first line current, the other currents will be the same magnitude, just phase angle is different. So this is what we have. We take the voltage divided by the impedance, we get the first line current, because this is phase A equivalent circuit, single phase equivalent circuit. Then after that, the other currents, you just take this angle, subtract 120, you get this. Plus 120, you get this. Okay? Because the difference between this first phase and the second phase in the source, first phase, for example, the angle was 0, the second one was minus 120, the third one was plus 120. So what you do, when you find the current in the first phase, the second phase current, it's the same equivalent circuit, the same voltage, the same impedances, the same thing, except the angle that is minus 120. So you're going to get the same magnitude, just minus 120. So what you do, minus 120, this minus 120, and this is plus 120. You got the three currents. This is another question when I'm going to actually do this and let you go. Maybe we can do a few things about the midterm before you actually leave. Okay, so here's the question. A Y connected source, and it is balanced. So Y connected source, I'm gonna do Y connected source. The voltage VA is this, 120 angle 30. And it says positive sequence, the source is positive sequence. It means the second one will be 120, and you're gonna subtract minus 120 degrees, so it will be minus 90. And the third one will be 120, and you're gonna add 120 degrees, so it's gonna be 150. This is the source. The source has internal impedance is this. It says it's a generator with impedance. Generator has impedance. So what is the impedance per phase? There is impedance, and it is connected to the generator, to the source. And this impedance, now this is the source. And this impedance is 0.4 and J3. Plus J.3. Same for the second one, 0.4 plus J.3. Then 0.4 plus J.3. So this is the Y connected load source. Then it's connected to Y load. So I'm gonna do the load. This is the Y load. Okay, it has 24 the impedance 24 plus J19. 24 plus J19 and 24 plus J19. This is the impedance per phase, and this is the load. Between them, they're connected with a line that has this impedance per phase. So I'm gonna put the line. This is the line. Has impedance. I'm just putting them in different currents so we can see where the line is. Oops. So this is the line until this point here. And the line has an impedance of 0.6 plus J0.7 ohm. Now these are ohms, by the way. And those are volts. Ohm. Same here, 0.6 plus J0.7 ohm. And the same here, 0.6 plus J0.7 ohm. So this is the circuit, this is the connection. Y source, Y load, line in between to connect the power from the source to the load. The line has impedance, the load has impedance, they're balanced, and the source has voltage and internal impedance. Find the line current. So this is exactly like the last question. So what I'm gonna do, first thing, let me just divide it into spaces. What I'm going to do is Y to Y, I'm gonna take single phase circuit. So what is a single phase circuit? Is this, starting from the neutral to the neutral. So I see source, impedance, impedance, and impedance. So it's a source, then impedance, then impedance of the line, then impedance of the load. Then what we have is the circuit completed. And this is the current IA, the line current here. This impedance is 24.J19. This impedance is 0.6 plus J0.07 ohm. They're all in ohm. This is 0.4 plus J0.3. And here it is 120 angle 30 volt. Plus minus, it's an AC source. Now this circuit here, I can simplify it, add all the impedances together. So they're gonna be one impedance. Combine all of them, they give me one impedance and one source. This is called, by the way, single phase equivalent circuit. Single phase equivalent circuit, okay? So I'm doing single phase equivalent circuit. Means I take one phase. And what happens in the first phase is gonna be the same in the second phase and the third phase. So take single phase equivalent circuit. So what is the impedance? I'm gonna add the real 0.4, 0.6, and 24. So this is 25 as real. I added the real component. With the J, 0.3, 0.7, that is 1, and 19, so it's plus J20 ohm. This is IA, and the voltage is 120 angle 30 volt. Now it's easy to see the current IA, just the voltage divided by the impedance. So IA equals to 120 angle 30 divided by 25 plus J20. And this is going to give me, I think, 3.75. And the angle is minus 8.6 or something volt. Oh, not volt, ampere. So this is single phase analysis. Once I'm done with it, khalas, I don't look at the single phase analysis. Forget about the circuit here. Now for me, now I start answering the question. So this analysis is just to find this current. Then I go back to the original circuit. So the line currents. So IA, IB, and IC. I just found it. So which is 3.75 angle minus 8.6, I think, ampere. Now IB will be 3.75. IC will be 3.75. This is a straight right away. Magnitudes are equal, balanced system. Now the angle, you're gonna, because it's positive sequence, you're gonna go minus 120 plus 120. So if I subtract minus 120 from this angle, I'm gonna get minus 128.6 ampere. When I add 120, it's gonna be 111.4 ampere. Now the load phase voltage, this is the second thing. Okay, the load phase voltages. So it means the voltage cross the load here. To find this voltage, V phase, Ohm's law, I phase times, let me just put here A and here's N, just to divide B and C. I phase, Z phase. Now I need to find I phase. What is the current in the phase here? It's exactly the same as the line current. The line current and the phase current is the same. So what they found as a line current here is going to be through the phase. If I multiply it by the impedance, I'm going to get the voltage cross the phase, cross the impedance, the load impedance. So I do VA, VAN, the first phase, is this current, 3.75 angle minus 8.6. This is the line current, but it's exactly like the phase current, okay? Because the line current equals the phase current here. But what I do phase current, not the line current, okay? Phase current. Maybe I should write that down. I'm gonna write that down because people will get confused before this. So I have to find the phase currents. So I can apply it here. So the phase currents, I phase 1 is going to be the same as this value, 3.75, because it's Y connection, phase and line currents are equal. Phase 2, phase 3. Because when I apply the phase voltage, I have to use phase current and phase impedance, phase current and phase impedance, phase current and phase impedance, okay? So I have to find the phase current. Sometimes it's not equal to the line current. 3.75, 3.75. This is just a step that repeating, because I'm afraid that at some point you're gonna apply the line current. No, it's the phase current. It happens this time, it is the 128. And this is 1.4 ampere. So now V phase A N, I'm gonna take this current multiplied by the impedance, which is 24 plus J19. The load impedance and the load current. Load impedance and the load current. The load current is the current going through the phase here. 3.75 and angle minus 8 point something 6. You get the voltage here, VAN, then you can find VBN and VCN. How? The same magnitude, just to change the angle. Can anyone do this in their calculator, these numbers? If you don't have the answer, if no one gives me the answer, then you're, whatever you get here, the magnitude is the same here, the same here. The angle minus 120 plus 120. Anyone with the answer? I got 114. I'm not sure about the angle though. 114.8. 114.8. 114.8. The angle 29. Maybe 29.8. So the angle here minus 120. So it's gonna be about 100. Plus 120 will be 149.8. Those are something to make sure to check. Okay. This question is important. Y-to-Y connection is important. The analysis is not difficult. Finding the line current, you take single phase, you find it. Then once you have one line current, you can find the other line currents, you can find the phase currents, you can find the phase voltages, you can find whatever you want. Best of luck with your midterm. And I'm gonna stop here so you can actually, some of you may be still home, they're coming, some needs some review. Make sure don't make things complicated. Make sure you try all the questions. You're gonna use sometimes voltage divider, sometimes you're gonna use Ohm's law, sometimes you're gonna just apply the steps of finding the equivalent circuit. The mesh analysis, you're gonna see current source, so make sure you know how to deal with the current source, okay, in one branch or in between, There's a slide showing how to do that in the lecture. Mesh analysis, the nodal analysis is gonna be one node only. It's gonna be one node, the reference and one node, and that's it. 10 questions. Some of the questions will take 3 to 5 minutes. Some might take you 10 minutes. You're going to have an hour and 30 minutes to do the test. Do your best. Any questions? Okay. I'll see you inshallah later today. Assalamu alaikum.